This is problem 937. It's on page 376. A pair of gears with 20-degree full-depth involute teeth transmits 40 horsepower while the pinion rotates at 1150 RPM. The diametral pitch is 6 and the quality number is A11. The pinion has 20 teeth and the gear has 48 teeth. The face width is 2 1/4 inches. The input power is from an electric motor and the drive is for a cement kiln. The drive is a commercial enclosed gear unit. Okay, now you guys will probably have to give me a little bit more calculator help than I would normally ask for in this problem because, like I said, we used to use Q numbers for quality, and that's the way the problem used to be specified, but the main change from the last edition of the book, bless you, is that the quality is listed as an A11 quality instead. So let me just jot down what we're given from the problem statement. The pressure angle, 20 degrees, and like I said, that's either going to be 20 or 25 degrees. In very rare cases, it might be 14.5 for analysis, but you would never design with 14.5 degree gear teeth anymore. So there's the pinion speed. The diametral pitch is 6 inverse inches. The quality number is A11. The number of teeth on the pinion is 20. Number of teeth on the gear, 48. And I'll double check all these numbers and make sure that they are still the same, but I think that's what we read. Let's see. 20 degree, 1150, 40 horsepower. So far, so good. 20, 48 teeth. Yeah, that's right. Okay, so if we read the problem statement, though, they haven't asked us anything yet. So the problem statement is at the beginning, as usual. There's one problem statement for multiple problems. For problems 36 through 41, compute the bending stress number, ST, using equation 916. Assume that the gear blank is solid unless otherwise stated. Let's see. Data in these problems are used later for basically pitting stress of the teeth, or pitting resistance of the teeth. Okay, now the first thing we need to do is figure out how much load is applied, because there's no way we can come up. Let me fast forward in the slides a little bit. Equation 916 that your author was talking about is this equation. The equation that gives you the bending stress number. Now, we call it a bending stress number because it's not a real stress. Okay, now why is it not a real stress? Do you remember?
It's at the max, isn't it?
It's not the max, it's actually more than the maximum. This is actually higher than the actual load you will observe in the gear material. And the reason it's higher is because it's got all these overload factors and bending factors and things that account for the way that the gear will behave in practice. Okay, so it's accounting for all the extra abuse above and beyond just the stress and how that stress is applied. Okay? But to get at this at all, we're going to need W sub T. What is W sub T again? Do you remember? T gives it away. It's the tangential load. What's a tangential load? Well, let's go back and look at it. It's the force. The force. Right? It's this piece, right? There's oil on the gear tooth, and so the force is always actually normal to the surface of the tooth. And so notice that normal force, it actually does not move around as the gear tooth rotates. That's the beauty of the involute profile, is that normal force remains at a constant 20 degrees. But anyway, the tangential component is just the piece that actually pushes on the tooth to make it turn, not the piece that pushes on the tooth to separate the gears. Okay, that's the piece that actually transmits power, is that tangential portion. To get that tangential portion, we have to look at how much torque is applied to the gear teeth, and that's here. But to get the torque, we have to go through power and speed. Okay, we're given power and speed. And let's remember the input's an electric motor, output's a cement kiln, and this is a commercial enclosed gear unit. Anyway, for the sake of the video, let me jot down the equation we're really trying to deal with. ST equals tangential load, diametral pitch, over the face width, over the geometry factor, J, overload factor, size factor, Km, I can never remember what it's called. I know what it is, but I can't think of it. Bending, or rim factor, and then the velocity factor. Let's start off with some geometry stuff. The diameter of the pinion, notice the the pinion and the gear are given, because we have the number of teeth on both and we have the diametral pitch. The diameter, or the pitch diameter of the pinion is 20 teeth divided by 6 inverse inches, and so that's 3.33 so on inches. Okay? Now, the tangential velocity is pi, diameter of pinion, speed of pinion divided by 12. Now, I could plug in the number of teeth over the diametral pitch, but I've already got the diameter, so I'll just leave it there. So pi, 3.33 inches, 1150 RPM over 12. What kind of units do you think we'll get out of this equation for velocity?
Feet per second?
Feet per minute, actually.
Oh,
Okay. Well, you can't really look at this, right? Because we've got inches here and RPM here, and yet we get feet per minute. That's what all these conversion factors do. So when you use an equation, and it's got conversion factors built into it, you have to know what units to put in and what units you'll get out. So as we use these equations, you may want to jot down some notes, if they're not already there, about what units go in and come out. So 1,003.6 is the number I got from my calculator, and that's feet per minute. All right, now the tangential load. If we wanted to, we could go through this equation that says power is torque times speed. And then we could use the equation that says, let's move down one slide, that the tangential load, W sub T, is equal to 2 times the torque divided by the diameter. Now, it wouldn't matter whether we use the pinion or the gear to do this, except that the torque we're talking about, the only one we could actually get, is the torque on the pinion, because that's the one where we know the speed, right? We only know the speed of the pinion, we don't know the speed of the gear. We could get it, and then get at the torque on the gear, but basically we're given more information about the pinion. Now, it turns out that there's another equation, and I'm not going to go through this. This would work fine when we get the same result. But there's another equation that's very convenient. It gives you the tangential load directly, and it'll be worth finding it in your book so that you can complete an equation sheet, or however you want to remember this, or mark it, or whatever. Let's see. Tangential load equation. Should still be here in chapter 9. Find it. Here we go. Go to page 323 and look at equation 9-8. Notice that equation 9-8 on page 323 is an equation that gives you the tangential load in terms of how much power is being transmitted through the set, okay, through the gear set. But go up one more equation to the top of the next page, equation 9-9. It's even more convenient for us because it has the tangential load in terms of power and tangential velocity, okay? So that will be the most convenient equation to use since I've already got the tangential velocity. So this is 33,000, equation 9-9, times the power divided by the tangential velocity. So that's 33,000 times 40 over 1,003.6. Now what units do you think we get out of this? Pounds. You have to look, right? Because you don't know what this 33,000 is. That's a conversion factor. To what units? Well, if you put it in horsepower and you put it in feet per minute, then you will get pounds force out of this. Numerically, it's 1,315.3 pounds force. So again, a lot of the equations in this book, you've got to know what units go in and what units come out. Okay? Because there's a lot of conversion factors just floating around. You have to know what they mean. Okay? So you may want to make some notes around equation 9-9. Anyway, there's the load. So there's over 1,000 pounds between mating gear teeth. So that's quite a bit of load. All right. So that takes care of one piece of this equation. Let's see, one down, 1, 2, 3, 4, 5, 6, 7, 8 things to go. Well, 2 of them are given, right? The face width and the diametric pitch are given, so that gives us 6 things to go. All right, so the geometry factor J, where do we get that from? Well, Chapter 9 has some very convenient charts in it. You can actually get the AGMA standard, and it'll have a whole lot more geometry factors in it, but for our purposes, page 336 is where we'll get all of our geometry factors for spur gears. So page 336. Notice that on this page there's an upper and a lower figure. The upper figure is for 20-degree teeth. You may want to highlight that if you highlight your book. And the lower figure is for 25-degree teeth. Now, how do you determine the geometry factor? Well, the geometry factor for the gear and for the pinion are different. Because look at it. The way you read this chart, the geometry factor that you get out is on the y-axis. You see that? I'll hold it up for the sake of the camera. So the geometry factor is on the y-axis. The number of teeth are on the x-axis, and the number of teeth in the mating gear are these lines. So you have to select the correct chart in the first place. So we've got 20-degree pressure angle. Which one do we want, figure A or B? Figure A, right? Because A is for 20-degree gear teeth. Now, let's say that we're interested in the geometry factor for the gear. Okay, so the gear has 48 teeth. So on the x-axis, we need to find 48. Now I see a 45 and a 50. You guys see that? So it's closer to the 50. So let's just go up the 50 line. How far up do we go? Well, we go up until we reach a number of teeth of 20 on the pinion. Because the pinion is the gear that's mating with the gear. Does that make sense? The pinion is the element mating with the gear, is the way I should say it.
The bottom one's the number of teeth the gear has, top one's
Right. So 48, or about 50, and then go up to about 20. Well, 17 is the lowest line, and 25 is the next one up. So about what do you think is the geometry factor?
3.9.
It's kind of hard to read off. It helps to have a little piece of paper, but yeah, 0.39, 0.395 seems reasonable. When I read it off, I guess I got a little cocky. I said 0.325. But that doesn't make sense, does it? No, I'm sorry. I'm reading the wrong. I read 0.395. There we go. I read it off wrong.
Sorry, this might be off the
That's
top.
all right.
Realistic value, we can read off, that's actually obtainable.
0.3, that's fine.
Okay. I didn't know if you were like,
No, as long as you've given me a reasonable number, I'm not too worried about it. So for the gear, 0.395 was the best that I could do. Okay. Now how about the pinion? I want you guys to try the pinion. So what you're going to do is take the number of teeth on the pinion, on the x-axis now, because that's the gear that we want the geometry factor for. So that's 20. Go up to the number of teeth in the mating gear, because the mate of the pinion is the other gear.
Is it
20 to a line 48. What's that?
Is it the number of teeth on the other gear or number of teeth that are going to be?
This, now that we're talking about the pinion, this is the number of teeth on the gear for which we want the geometry factor. So this is the x-axis. So go to 20 on the x-axis. Now you go up to the number of teeth in the gear that's mating with the gear that you want the geometry factor for. Okay? So now go up to the line that's 48. Well, there's probably not a line for 48, but there is a line for 50. So a little bit below the line for 50.
I got 0.33.
Yeah.
that's a pain to read.
Yes, it is.
You need like a credit card or ruler.
Well, the piece of paper works pretty well.
Sure. Credit card, yes, I think that's certainly issue.
Now, I chose 0.325 because it's just below that line for 50. So, right, wrong, I don't know. Close enough for what we're doing, yes. These are dimensionals. But notice they are different. Now, what do you think that does to the stress estimate, or the bending stress number, as we call it, for the gear versus the pinion?
Gears
Yes?
are smaller.
What's that?
The gears are smaller.
That's right. So the estimate for the stress in the gear is going to be lower than the estimate. That always happens. The pinion is always the more critical gear. It's the one that has the higher bending stress number.
Did they, I'm trying to think for application, like starting gear for on a problem. Is that generally a harder material or a softer material?
Usually the pinion is a harder material.
Okay, that's what I thought. I didn't know if they wanted to make that wearable gear or.
Well, you know, you got another thing to think about there, and that is
Because
which
it's
one's
easier.
easier to replace,
Sorry.
the Bendix or the
Yeah.
flywheel, you know? So, I mean, in that case, you may want to make the pinion the softer one and, you know, let it wear out.
Because taking a follow means pull the transmission.
Right.
I was just curious in that application. If it makes sense.
Okay, so we've got dimensional pitch, face width, and now we have geometry factor for both the pinion and the gear. And you see that we're going to have two different numbers. We're going to have an STP and an STG, two different numbers. Now, a lot of times we'll just go and analyze the pinion and be done with it, as long as we're going to make the pinion and the gear from the same material and the same processes. So let's just continue, see what we've got. We need the overload factor next. We'll just go in order. Where does the, what's that?
If they are different materials, can you still do that the same way and just do the x-axis and y-axis the same?
If they are different materials, you would still end up with the same geometry factor, but there are other factors that will be different. Or maybe not other factors that are different, but since the material is different, you're going to compare the bending stress number to a different material number, a different SAT prime. All right, so let's see, KO, overload factor, page 338. What do you guys think is the correct or reasonably close overload factor for this problem? The motor is an electric motor. By the way, for those of you that just came in, we're looking at problem 37 of chapter 9. So the motor is an electric motor, or the driver, the prime mover is an electric motor. What's being driven is a cement kiln. Now, don't think of a tub on the back of a cement mixer. It's not that sort of thing. A cement kiln is a much larger thing. I'll show you a picture of one. I live by a kiln, basically.
Oh, yeah, that's right.
Speed, they make, S-Rock makes cement there.
That sounds.
That's a kiln.
So you want to go with the biggest one?
Not necessarily. An electric motor is the drive. That's a fairly smooth drive.
Yeah.
But the stuff inside is going to be dropping,
Yeah.
right? And so there's going to be some shock associated with that. Now, when I looked at this, I decided power source, uniform, and then driven machine, heavy shock. Now, how do you decide that?
When in doubt, go big.
What's that?
When in doubt, go big.
Can, but notice that's going to change things quite a bit. If you just go big on something like this, you're going to end up out of business, right? Because you've got to be competitive. So, on the other hand, if you have too much downtime, then you're going to get fired because the machine's not working that you designed. Now, this is an interesting topic because you may wonder, well, what factor should I use? How would I decide? Whatever industry you go into, if you specify a lot of gears, the company will already have done this in the past, and they'll already have either their own training or their own guidelines they want. Okay, it's fairly common. But go back to page 337. For the sake of this book, there's something to help you with your selection. Notice in the left column under overload factor, where it says uniform light shock, moderate shock, there's a description of the various prime movers and where they fit. Okay? And then examples of the roughness of the driven machine include the following, and then it goes through uniform all the way through heavy shock. If you'll notice, under heavy shock, let's read the descriptions. Rock crushers, punch press drives, pulverizers, processing mills, tumbling barrels, that's the closest so far, wood chippers, vibrating screens, railroad car dumpers, log conveyors, lumber handling equipment, metal shears, hammer mills, commercial washers, heavy-duty hoists and cranes, reciprocating feeders, dredgers, rubber processing compactors, plastics extruders. the closest, if you read the other description, heavy shock sounded like the closest to me because they mentioned tumbling barrels. So I thought, well, that sounds a lot like a kiln, so that's why I chose an overload factor of 1.75. A uniform driver, heavy shock load. All right, what's next? Well, KS, the size factor is next. All right, KS, the size factor, how do we determine that? Well, the size factor, got it in my notes somewhere, I thought. The size factor is usually 1. Let's see, and it looks like I just assumed that and didn't bother showing why that is. But if you notice, we'll read this section on page 337. The AGMA, the American Gear Manufacturers Association, indicates that the size factor can be taken to be 1 for most gears. But for gears with large sized teeth or large face widths, a value greater than 1 is recommended. Reference 20 recommends a value of 1 for diametral pitches of 5 or greater, or for a metric module of 5 or smaller. For larger teeth, the value shown in table 9.8 can be used. So you'll notice we have a diametral pitch of 6 that's greater than 5, so KS is just 1. Now that's what usually happens. Usually the size factor is 1, because you usually don't deal with gear teeth that are extremely large.
So I have a feeling you're going to say, this is going to be on the test, and you're going to say exactly a description of one of those.
Well, if you're wondering what should I choose, go over to page 338, look at table 9-8.
Yeah.
And that's where the size factor as a function of diametric pitch and
I
metric
meant for
modules.
KO, like how getting the service factor, how you said light load or uniform loading,
Mhm.
minor shock, I feel you'll probably have an exact one.
Yeah, I usually do like to have an exact one.
Yeah.
Yes.
It's not up to us, I guess.
Right. Now, for the design projects, I like to have them more open and flexible. We have to
See
think.
what we take.
Yeah. Okay, so there's the size factor. Now for the KM, the mesh alignment factor, or load distribution factor. I always mess that up. CMA is the mesh alignment factor. PF is the pinion proportion factor, and I always call KM the mesh alignment. That's not wrong. It's a load distribution factor. There's two different factors at work here. But I'll just read what your author has to say. Any of the following factors can cause misalignment of the teeth on the pinion relative to those on the gear. Inaccurate gear teeth, misalignment of the axes of shafts carrying gears, elastic deformation of the gear, shafts, bearing, housing, support structures, clearances between the shafts and the gears, the shafts and the bearings or the bearings and the housing, thermal distortions during operation, crowning or in relief of gear teeth. All these things play into exactly how those teeth are interfacing with each other. Does that make sense? Okay, it's a very complicated thing. We're going to simplify it a lot for this class. Okay, so go over one page and you'll notice that the equation given is 917. And equation 917 says that this factor, this mesh factor, is 1.0 plus the mesh alignment plus the pinion proportion factor. And I've got these two flipped from equation 917, but you get the idea. Okay, so for the pinion proportion factor, this one, it says see figure 916. If you look, figure 916 is on the same page, page 338. It's the first figure. And basically all you have to do is figure out the ratio of the face width to the diameter of the pinion. That'll tell you what gear you're on, and then look up the face width on the x-axis, and you can read off the pinion proportion factor. Now, there's also equations off to the side, so you can use the figure or you can use the equations. You should get the same thing. Let's try both and see what happens. All right. Grab your calculators, if you would, please, and take the ratio of the face width to the diameter of the pinion. I just erased the diameter of the pinion, but I've got it in my notes. So face width to diameter of pinion, 2.25 inches. The diameter of the pinion, I think, was 3.33 repeating inches, right?
0.675.
Okay, 0.675. Okay, thank you. So the line we'd be on would be between 0.5 and 1. Now notice that there's some notes for which equation to use. It says when the face width is less than an inch, use the first equation. When the face width is between 1 and 15 inches, use the second equation. Now our face width is 2.25 inches, so we'd use the second equation. Okay. Now, also, we're going to use the chart, so let's finish up with the chart first. We've got the face width to diameter of pinion, and now we should be able to read off our pinion proportion factor. So, like I said, we're between the curve of 0.5 and 1, basically a little bit above 0.5. The face width is 2 1/4, so that's going to be between two minor lines on this chart. And so it looks to me like we should get a number of a little bit less than 0.05. You guys see that? You agree? So less than 0.05 should be our pinion proportion factor. Let's do it this way. Now let's use the equation and see what happens. The equation says take the face width over 10 over the diameter of the pinion, subtract 0.0375, add 0.0125 times the face width. Okay, so grab your calculators and try this, make sure you can get it. 2.25 over 10 over 3.33 repeating. I'm not going to put in the units. 0.0375 plus 0.0125 multiplied by 2.25 inches. Okay. Remember, we should get a number less than 0.05. At least that's what we think from the chart.
0.058.
That's what I got, was 0.0581. So what I assumed is that I just read the chart incorrectly, and I was just too inaccurate in reading it. Or maybe the distance between these curves is nonlinear, which doesn't make sense because it looks like they're laid out linearly. For whatever reason, there seems to be a slight disagreement between the equation and the chart, so I just went with the equation. Okay. So the pinion proportion factor, 0.0581, is what I got from this equation as well. Okay, questions so far? All right, but that's not all there is to it. We also have to get the mesh alignment factor. And for that, you go down one more chart to figure 917. And here you have to know what kind of gearing you have. Do you guys know the difference by the descriptions between open gearing, for example, and an enclosed gear unit? What do you think the difference is between those? Let's say that on your project, on your drift track project, you had chosen to use, let's say you had chosen to use gears instead of a chain drive. I would call that open gearing. Because basically what you've done is mounted a shaft on a frame. You've aligned it the best you can, but it's probably not terribly precise. Okay, that's open gearing. You can imagine there's going to be a lot more misalignment between something like that and something where, say, a transmission housing, where it's been precision machined so that everything is aligned very precisely and very accurately. Okay, so that's the difference between them. Now, whether or not you're talking about a commercial enclosed gear unit versus an extra precision enclosed gear unit, there's a little more leeway there. But if you've been in industry, you will still know the difference between this. A precision enclosed gear unit will be something that's usually used for motion control. For example, let's say you want something on a CNC machine. Okay, you're going to want an extra precision enclosed gear unit. You'll want something extremely precise, probably something even better than that. But for robotic applications, these are the kinds of things where you'd go up to the extra precision enclosed gear units because they're going to be very, very precise. Okay.
Does it matter if it's, or I guess it matters. How would you line up a gear? I guess there's tools for it and everything.
Well, the key is to line up the shafts and make sure the shaft's
They're
straight.
parallel.
Yeah. Well, the shaft also has to be straight.
Yeah.
But yeah, I mean, it's just more precision machining than anything. Have you guys used coordinate measuring machines before?
Yeah. They do it on prints, coordinate measuring.
Yeah, CMM is a coordinate measuring. Well, it's one of the things that I wish we had in our lab that we don't. We've got a lot of make stuff, but we don't have any test. Well, we've got a little bit. You can pull specimens apart and things. But a coordinate measuring machine is something I think you guys will encounter very quickly once you get out in industry. They come in all shapes and sizes. They used to be ridiculously expensive, and only the big players had them. Nowadays, everybody's got a coordinate measuring machine. Basically, what you do is you lay a part down. You you bolt it down, you tie it down where it's held down very firmly.
Yes, firmly.
And you touch points, it has a point, you know, a probe, yeah, and you just measure various points and it interprets the geometry. It can actually tell you how out of round a circular feature is. It's so precise. So anyway, they're very good tools, very good, and it's a whole lot easier than messing with a pair of calipers trying to get, you know, you can't really get geometry from a pair of calipers, whereas you can tell how straight a line is or how round something is with a CMM. Of course, there's varying qualities in those too, but
Our
they're
CMMs, like, they're really high, or really expensive.
used to be. They've come down in price a lot in the last 5 or 10 years. And really, even before that, I worked for Banjo Corporation, I think I told you guys. They had a coordinate measuring machine, and that was back in 2000, so.
What are they called?
Coordinate measure machine.
Coordinate measure.
Yeah, coordinate, CMM. Okay, so the mesh alignment. Well, fortunately, we were told what type of gearing that this was, and they said it was a commercial enclosed gear unit. Okay. So we know which curve to be on or which equation to use. Again, I usually like to use the graph first to make sure my equation comes out right. Since the face width is 2 1/4 inches, I'll just go up to the line for commercial enclosed gear units. X-axis 2.25 inches, and I'm on figure 917. What number does it look like I would get? What do you think?
1.6.
Yeah, something above 0.15, right? Okay, now let's try the equation. So CMA, the mesh alignment factor, is 0.127, just reading the equation off to the side, plus 0.0158 times the face width, less 1.093 times 10 to the negative fourth times the face width squared. Of course, I'm going to plug in 2.25 inches for both of these. Okay. And when you're done with this, you get 0.1620. So that takes care of the mesh alignment factor. Now, notice something here. We don't have these equations for metric. We only have these for English gears. So if you tried to apply this to a metric gear, you'd have to change the face width to inches because this equation expects inches. Okay? Other than that, it should work out. All right, now let's see. If we add all these together, then I came up with 1.2201 for the, see, I can never remember it, KM. I don't know why I've got a block on that. Load distribution factor. So 1.2201 is the load distribution factor. Question so far? Okay, now KB, do you guys remember what KB was all about?
Thickness of the gear or thickness of the teeth?
It's not the thickness of the gear, it's the thickness of the rim that the teeth are mounted on. Okay, it's a ratio of those two. Now, there was one thing they told us. They told us that these were all solid gears. Remember that? So there is no rim. The rim is basically as thick as you want it to be. We go all the way down to the center of the gear. So in that case, what that means is that the rim, the effective rim, is much, much thicker than the height of the teeth. So basically, this is going to be 1.0. It's fairly common that the size factor and the rim factor come out to 1. Okay. Finally, the velocity factor. This is where I'll need the most help. Oh, by the way, the backup ratio, if we were to try and compute the backup ratio, it would be a number greater than 1.2 because the effective rim thickness would be so much larger. Anyway, velocity factor. Now, the reason I need help here is because the old way involved Q numbers instead of A numbers, so we'll have to figure out how to do this. Page 341, though, is where we're at. Now, we were told that we have an A11. What that means is that it's that AV equals 11. And so you can see which curve we're on. We're in the upper figure because we're dealing with U.S. customary units. And you can see what curve we're on. Now, the x-axis is the pitch line velocity. That's why I calculated the pitch line velocity early on, because I knew I would need it over here in the velocity factor. And the pitch line velocity we got at that time, let's see, looks like it was 1,003.6 feet per minute. So basically 1,000. Okay, close enough to 1,000 to call it 1,000. So that makes it easier to read off this chart. Now, if you look at 1,000 and go up to the curve for A11, what number do you get for the dynamic factor, KV?
1.43.
I agree. I was going to say 1.42, 1.43, close enough. Now, the thing is that we can get a more accurate estimate than this. Now, this may be a little confusing, but look on the left page, table 9-9. There are equations here that do the same thing as the charts. The equations in the left-hand side of the table are for U.S. customary units. The equations and things in the right-hand column are for metric. Okay, so let's go over to the U.S. units. Given AV and V sub T, we have to calculate B. And the equation for B says take a quarter of AV less 5 and raise it to the power of 0.667. So grab your calculators and do this if you would. So this number here, AV, is going to be 11. I've got the old method in my solution using the QV number. I'm not used to having a calculator in class. I can do this as well. Okay, let's see. So 6 power of 0.667 multiplied by 0.25. What did you guys get?
0.826.
That's what I got. 0.82. Well, yeah, 60 really, if I rounded properly. So there's B. Now, what good does that do us? Well, it'll help us in just a minute. We have to calculate C as well. C is 50 plus 56 times 1 less B. Okay.
59.8.
You already got it? How much was it?
59.8.
59.8, thank you. Now we have to calculate the dynamic factor KV based on these two numbers, and it's just C over C plus the square root of the tangential velocity to the power of negative B. Okay, so let's see what we get. Now VT, it's in feet per minute, and it's 1,003.6.
I got 1.42.
I agree. So this comes out to 1.42, and we'll just round it off there. Okay? So we were right in there. We were close enough. But like I said, if there's a chart, I always like to use it to compare because I know I can hit a wrong button on the calculator and never realize it. Okay, so we've got everything we need to put into this equation. Can I erase this, or you okay? As I said, I always post my example problems too, and if I forget to post them, remind me and I'll make sure they're up. Anyway, so the tangential load, let's see, we should be to the point where we can finish this thing off. 1,315.3 pounds force. 6 inverse inches for the diametral pitch, 2 1/4 inches for the face width, 0.325. Notice I'm going for the bending stress factor for the pinion, or the bending stress number, I mean, for the pinion, because I plugged in the geometry factor for the pinion.
That's the one that's going to matter, right?
That's the one that's going to matter if they're both from the same material. Okay, the overload factor, 1.75. Size factor 1, we'll just leave that off. 1.2201 for the alignment factor. And then KV, 1.42. Okay, I left the bending factor off also since it's 1. Now the number we get here is going to be slightly different from what I had in my solution when I worked it out in the 4th edition of the text. So let me type it in. Times 1.2201 times 1.42. There we go. Okay, bending stress number 32,721.4. If you want that in any decimal places, PSI. Do you think it's warranted to have this 4 here? How about the 1? How about the 2? How about the 7? Probably not, right?
33,000.
33,000 or so is still kind of a shot in the dark. Now, if you don't want to make the gear of the same material, it's really easy to get the bending stress number for the other one. All you have to do is take the bending stress number you already have and scale it by the J, because everything else is the same. The face width, the load, all this is the same. The only difference is the geometry factor. So take, let's see, divide this by the geometry factor for the pinion, and then, let's see, no, that's wrong.
Multiply by that, right?
Yeah, multiply by.
You like the ratio of the pinion over the gear.
Exactly. Yeah, you got it. Okay. So when you do this, it'd be 32,721, I guess we'll just go ahead and use it, times 0.325 divided by 0.395. Okay. So let's see, answer times 0.325 over 0.395. And I get 26,923 or so PSI. Okay, was that a long problem? You want some encouragement or discouragement? There's both in this.
It's useless.
Pretty much. See, gear teeth don't fail due to bending most of the time. They fail due to contact stress. That's the bad news. You have to check this anyway. Okay, it's just sort of due diligence to say you're going to check this. The good news is most of these things will come into play again when we talk about the contact stress, because it's the same load, right? It's still this tangential load that's causing pressure between the gear teeth. Okay, so if we're considering the surface of the gear teeth now, all this stuff is still important. There's just a few things that change. Principally, the geometry factor changes, and then depending on whether we're talking about spur gears or helical gears or worm or bevels, then the form of this changes. But a lot of these factors stay exactly the same. So we get to reuse a lot of this stuff. Make sense? So we're going to work a problem a little bit later where we work with this same gear set, look at the surfaces to make sure that they will last, right? Because we need a stress estimate on the surface, not just at the root of the tooth, because that's really what this is. This is the bending stress at the root of the tooth, pretending that the tooth is like a cantilevered beam. Okay, so we'll also get a stress at the surface of the tooth and make sure the material can take both of those. Now there can be a significant difference in the gear, whether you're talking about the root of the tooth versus the surface, if you do something like case harden the gear. Do you guys know what case hardening is? Basically the outside shell of the thing is hard and the inner is soft. And that's usually a good thing. It usually makes it more ductile.
Harder on the outside and tougher on the inside. We have a test over today, so.
What is it?
We have a test over today, so I know that.
Okay, all right, yeah. So anyway, we have more work to do. We have to do this anyway. We're going to reuse a lot of this. So the other bad news is we're not even halfway done with this gear set. Okay, all we've done is gotten the bending stress. We still have to get the contact stress. And then we have to select a material and apply a bunch of modifying factors to the material. All right, I'm going to make some notes about this. Why don't we take our break and then we'll come back.